In this video, we'll begin a review of the method of partial fractions for decomposing rational expressions, like the one I have here, into terms which are easier to integrate. The first case that we'll talk about is when the denominator decomposes into distinct linear factors. In this case, x squared plus 2x minus 3 can factor into two linear factors. We'll have x minus 1 and we'll have x plus 3. That means the decomposition into partial fractions will have two terms. One of them will have the x minus 1 in the denominator, and at this point an unknown constant, a number, which we'll call a. Then we'll get another term, x plus 3, corresponding to this denominator, or this factor, and it will have some unknown numerator that we'll have to figure out. Let's call it b for the time being. In order to find what a and b are, we'll take this equation that has on the left side this rational expression, on the right side the two terms, and we'll clear the fractions by multiplying both sides by that common factors, the product of the two factors that appear. So we'll multiply the left by the x minus 1 times x plus 3, and we'll have to do that to each term in the right. So I'll do it to the first term and also to the second term. When I do that, on the left side, everything will clear away. I won't have any more denominator. That was the goal. On the right side, one factor will cancel, in this case the x minus 1, and you'll be left behind with an x plus 3. In the other term, the x plus 3's will cancel, and you'll be left with the x minus 1. What we now do is compare the left and right-hand sides. I'm going to distribute everything else out and look at the coefficient now of the x term. If I multiply, I'll have ax plus bx, so I'll have a plus b x's. I then do the same thing for the constant terms. I'll have 3 times a, and I'll have minus 1 times b, so that will give me 3a minus b for the constant terms that have no x's in them. I then compare the left and right-hand side. A plus b, which is the coefficient of x, must agree with the coefficient of x on the left-hand side. So a plus b should equal 3, and I now have an equation in the two variables a and b. I need one more equation to make progress, and I'll do that by comparing the constant terms. So I'll take 3a minus b, compare that to the 17 on the right-hand side. Those have to agree, and I now have a pair of linear equations in the two unknowns, and I have two of them in two unknowns, so I should be able to solve for a and b. In this case, it's probably easiest just to add the two equations together and eliminate the b. I have plus b and minus b here, so if I add them together, I get a new equation which has to be valid. 4a is equal to the sum on the right side, which is 20. So that tells me that a has to equal 5. I can then take that value, plug it into either of the equations. I'm going to take the first one here, solve it for b. I get b as 3 minus a, and then I can plug in the value of a that we just discovered, 3 minus 5, so b is equal to minus 2. I can then go back up to my partial fractions. We know that a is 5, so it breaks down into 5 over x minus 1, minus 2 over the x plus 3, and this expression here is called the partial fractions decomposition. Why we might do this is so that we can integrate the expression. The original rational expression looks very complicated and difficult to integrate, but if I rewrite it in terms of its partial fractions, it becomes something much simpler to integrate. I can go term by term now, and I'll have 5 times the log of the first denominator minus 2 times the log of the second denominator. Don't forget your constant of integration, and we have an antiderivative for the original expression. Just as good practice here, because it occurs in many applications, we can rewrite these expressions. If I have a 5 in front of a logarithm, it becomes the log of that expression to the 5th power. And if I have a 2 in front, it will become that expression squared, and when I'm subtracting logarithms, it's going to be their quotient in the logarithm. So we ought to be able to use our properties of logs to rewrite this expression as a ratio and then the log. And again, don't forget the constant of integration.